Hello everyone and welcome. My name is Petr Štibinger and I'm the lead author of the paper on mobile manipulator for autonomous localization, grasping and precise placement of construction material in a semi-structured environment. On behalf of the authors and my colleagues from Czech Technical University, University of Pennsylvania and New York University, I will now present you our work. The main motivation behind this work was the automation of a construction work. During this task, no human interaction between the robot and other workers was allowed, and the robot was to navigate through a semi-structured environment to locate, transport and place well-defined objects of interest, such as bricks, which were placed in a previously unknown location somewhere within the area. One of these scenarios was also tested during the Mohammed bin Zayed International Robotics Competition in 2020. This competition aims to push the boundaries of robotic research with complex challenges, and one of these challenges included a model construction site to be explored by the robots and a series of tasks to be fulfilled. I will follow the task description from the Mohammed bin Zayed International Robotics Competition as the task description for this work. The area to be explored was around 50 by 60 meters of rectangular shape with mostly flat ground, and somewhere in this arena were 4 brick classes of various shapes and weight. These bricks were arranged in a pickup area in 4 stacks, divided by their colors and properties. There was also a placement area consisting of a yellow and magenta checkered pattern, which was flat and placed on the ground. And during this challenge, 3 aerial vehicles and 1 ground vehicle were to be deployed in this arena to fulfill a series of tasks. In this work, we focus only on the ground robot, so the objects of interest for the aerial vehicles are treated as obstacles. The time limit to fulfill this challenge was 30 minutes, and the task consisted of localization of the bricks, their pickup, transportation, and placement onto the checkered pattern in a pre-specified order. The robotic platform we used in this challenge was built on the ClearPath Robotic Husky A200 mobile base, which was attached to a Kinova Cortex Gen 3 robotic manipulator, which you can see is the white arm here in this image. We used the model with 7 degrees of freedom, which gave us plenty of mobility for the manipulation with the construction material. We also used Intel RealSense D435, which is an RGB and depth camera, which was mounted onto the gripper of the arm, and a Velodyne PUC VLP16 LiDAR, which was mounted onto the mobile base and provided us with the necessary information of the robot's surroundings. We used Intel NUC i7 as the onboard computer, running operating system Ubuntu and the robot operating system. For the brick manipulation, we utilized a custom-built gripper with 2 electromagnets. These magnets were also equipped with Hall effect sensors, and we used an Arduino Nano board for power management of the magnets and data readout from the sensors. This Arduino board also provided us with an USB link to connect the gripper to the onboard computer to provide us a full control through the robot operating system. The gripper was also loaded with a spring dampener to soften the impact of the gripper onto the bricks. We mounted the RealSense D435 to the gripper directly so that we could use the camera for visual servoing later during the brick grasping. We also utilized the Cortex interface for the robot operating system, which was provided with the arm by the manufacturer, and we used the MoveIt motion planning library for joint space commanding of the arm. The motion planning was further supported by declaring a no-go zone around the mobile base, which was dynamically adapted to accommodate the payload, because the robot was equipped with a cargo bay and could store up to 7 bricks and it was necessary to avoid the already loaded bricks in the cargo bay in order not to knock them off the robot. The localization and navigation was handled by the ROS navigation stack as implemented by the Strands project, and we utilized the point cloud provided by the Velodyne PAC sensor to provide us the information about the robot's surroundings, the arena, and to localize its position. We split the point cloud into two horizontal slices. The lower one was used for dynamic obstacle avoidance, so this represented the nearest objects to the robot, and could also include dynamically occurring objects such as bricks dropped by the other aerial vehicles or the aerial vehicles themselves. And the upper part of the point cloud was used for the navigation and localization of the robot within the arena. We also utilized a high-resolution 3D scan for data augmentation, which we obtained by a Leica 3D scanner prior to the deployment. To determine the position of the robot within the arena, we utilized the adaptive Monte Carlo localization, which fused the wheel odometry and the LiDAR data to localize the robot. For the brick stack detection, we used the estimate from the LiDAR data for coarse estimation. This point cloud provided by the LiDAR was processed by the iterative endpoint fit algorithm to extract line segments, as you can see in the picture on the upper right. Since we knew the brick dimensions in advance, it was fairly simple to extract the segments of the corresponding length. And we also knew the layout of the brick pickup area, so the arrangement of the colored piles in advance. So we also utilized a Gaussian mixture model to determine the position and orientation of the pickup area. The Gaussian mixture model is shown on the bottom right, and this model was used by an estimation maximization algorithm to provide us the position of the overall pickup area. As you can see on the picture on the bottom left, here are the first 5 iterations of the position of the red bricks, and as you can see, after only 5 iterations, the coarse estimation was fairly close to the ground truth, which is marked by the orange cross. The reliable detection range was around 6 meters with the LiDAR sensor with only 16 horizontal lines, and this was sufficient for this task. After successfully navigating to the brick piles, the robot would extend the arm so that the camera mounted to the gripper is pointed directly towards the ground, and during this phase the robot would align itself precisely with one specific brick to be grasped. We used tight coupling of the control of the mobile base and the manipulator arm so that we can maximize the accuracy of this alignment. We utilized the depth channel of the camera stream and used a flood fill image segmentation algorithm to quickly extract the corners and the centers of the segments within the image. At the bottom left you can see the RGB stream from the camera for reference. At the center is the raw stream from the camera, and at the lower right is the segmented image after it was processed by the flood fill algorithm, with annotated corners and center of the segments extracted from the image. Utilizing the depth channel also allowed us to directly transform the extracted corners and centers of the bricks into 3D, so that we had direct coordinates for the arm to navigate to during the grasping process. In the alignment, we were able to achieve accuracy within 2 centimeters. After successfully loading the bricks into the cargo bay of the robot, we then navigated through the arena and looked for the placement pattern, which was marked by the yellow magenta checkers. We utilized the wrist-mounted RGB camera, which the robot extended upwards, and searched the surroundings for this pattern. We also utilized the flat film segmentation algorithm, which was modified for this task to work with RGB data and also to bypass corners so that we can extract the checkers as one continuous segment, as you can see at the image on the bottom right. Since the pattern was flat and the squares were quite small, the robot was unable to detect the pattern reliably beyond 4 meters from the camera. So we had to utilize the images taken from above. We also experimented with communication with the drones to directly send the information provided from above within the shared arena. This we approached in the way of guided autonomy, where the drones or a human operator could provide an estimate position of the pattern for the robot to explore, which could be provided within the detection range plus minus 4 meters, and the robot would then navigate towards the pattern and explore this area. If this attempt would be unsuccessful, the robot would then continue with exhaustive search of the entire arena. Before the competition, the main development was taking place at the New York University campus in Abu Dhabi, and afterwards during the Mohammed bin Zayed International Robotics Challenge. At the bottom you can see a table showing accuracy of the brick classification provided by the iterative endpoint fit algorithm, and as you can see, the algorithm was fairly successful in extracting the red, green and orange bricks. The most difficult for the algorithm was to extract the blue bricks, which were also the least numerous and were easily confused by other objects in the arena. Luckily, the blue bricks were located in between the orange and the red piles, so that the expectation maximization algorithm using the Gaussian mixture model could easily filter out the false detections. 32 teams participated in the competition, but only 2 of them managed to score points with their ground robots in autonomous mode. The biggest difficulties encountered by the teams during the competition were on the sloped ground plane, which ran through the entire arena and introduced false detections in the laser-based localization, and it also increased the difficulty of brick grasping and loading. After a series of unsuccessful attempts on the first competition day, our team decided to pick up only one red brick and deliver it straight to the placement pattern on the second competition day, which was successful, and we were also the only team to score points in autonomous mode with both ground and aerial robots during this competition, which yielded us the victory. If you're interested in more videos and photos from the competition, as well as the source code we used with the ground robot, you can visit this website to learn more. We would like to thank the Czech Science Foundation, the Czech Technical University, and the European Union's Horizon 2020 Research and Innovation Program Aerial Core for supporting our work. We are also grateful to the Khalifa University for hosting the challenge and sponsoring the teams participating in its finals. Thank you for your attention, and if you have any questions, feel free to ask.